This example has us encounter a medical research team that is conducting a study to test the effect of a cholesterol-reducing medication. Right off the bat, by the way, when I start reading this, I say, oh, a medical research team for this. That level of significance for this hypothesis test better be small, because there are people's lives on the line here. Nonetheless, at the end of the study, the researchers found that of the 4,700 randomly selected subjects who did take the medication, 301 of them died of heart disease, whereas of the 4,300 randomly selected subjects who took a placebo, 357 died of heart disease. So the question is, with a 1% level of significance, which is quite low, so that's good, can we support the claim that the death rate due to the heart disease is lower for those who took the medication than those who took the placebo? This actually is a fairly realistic type situation where this type of statistics actually comes into play. Because what we see is, on the surface, it seems like more people were saved by the medicine, but they also sampled more people. So the question is this actually indicative of any significant change? That's what we're going to test. And this is the type of situation where hypothesis testing is really important, because people's lives are on the line, and you know this medical company is spending millions, if not billions of dollars on this type of research. So let's take a look and see if we can or cannot support this claim. To begin with, we have to do the same thing we did last time. We have to verify our hypotheses, and then we're going to have to compute the weighted estimates. So to begin with, we have to note two things: that the sample is random and that the sampling is independent. Of course, the subjects in one sample and the subjects in the other sample are different subjects, so that guarantees independence. And in terms of it being random, it does indeed say that the 4,700 and the 4,300 were selected randomly. So that's the first thing we're going to note. We're going to note that the samples are random and independent. The next thing we need to do is figure out what our weighted estimates are, P bar and Q bar. But remember, that required the X1 and the X2, right? So the formula for that said that X1 was equal to N1 times P1 hat. Notice here that for the first sample, we know the N1, it's 4,700, but we don't actually know the percentage of people that died of heart disease. We only know the actual number of people that died of heart disease. This 301 is actually representing X1. And so this is somewhat different from the previous problem. In the previous problem, we were given the percentage and we had to find the number. Here, we're given the number, and so we have to find the percentage. So it's somewhat different. Still using the same formula, but we're solving for a slightly different value. Nonetheless, we're still going to put this all into a table. We're going to have the table, let's see, we're going to have the people who took the medication and the people who took the placebo. The people who took the medication, how many took it? 4,700. Well, that's how many we sampled who had taken it. And the placebo, we sampled 4,300 people, where here the information provided to us actually gave us X values. So X1 was 301 and X2 was 357. And so you might think this is maybe a waste of time, because you can compute the P bar and the Q bar with just the X1 and X2 value. But we do actually need the P1 hat and the Q1 hat, or the P1 hat and the P2 hat, because that'll become relevant when we actually compute the test statistic later, like we did up here. So we are going to write that down. Let's see, the P1 hat, how do we compute that? Look at this formula up here. It's clearly P1 P1 hat is equal to X1 over N1. And so if we compute that quotient here, we're going to get a very small number. We're going to get 0.0640, and P2 hat is going to give us 0.0830. So again, we're not going to use that information right away, but we are going to need it eventually. What we do need right away are the N1, X1, N2, X2, because this is going to allow us to compute our weighted estimates. So P bar, which remember the formula for P bar is X1 plus X2, so the sum of the X's over the sum of the N's. X1 is 301, X2 is 357, whereas the sample sizes are 4,700 plus 4,300. This is giving us 658 over 9,000, which if we take that quotient, we're getting approximately 0.0731. So this weighted estimate P bar is going to take the place of any time we needed the population proportions for either of the samples. This is sort of a weighted estimate for both of them. And of course, Q bar is computed by taking 1 minus P bar, so that's 1 minus 0.0731, which is 0.9269. These computations are enough for us to now verify the last bit of the hypotheses, which is that the products of the sample sizes against the weighted estimates are all definitively greater than or equal to 5. Now, of course, the very large sample sizes here will probably guarantee this, but nonetheless, we really do want to check it and make sure we satisfy those. So what do we want to check again? We want to check N1 P bar, which in this case is 4,700 times P bar, which is 0.0731. If you do this computation, you should get 343.57, clearly larger than 5. Do the same sample size, N1, but against Q bar. So we're going to get 4,700 times 0.9269. That's going to give us 4,356.43. That's clearly larger than 5. And then we're going to do the same set of computations, but with the second sample size. So that's going to be with N2 P bar and N2 Q bar. N2 P bar is going to give us 4,300 times 0.0731. That looks like it's giving us 314.33, which is greater than or equal to 5. And N2 Q bar is giving us 4,300 times 0.9269. This is giving us 3,985.67, which is, again, greater than or equal to 5. So indeed, we find that not only are the samples random and independent, but that the 4 required products to have a normal distribution for our sampling are all indeed verified. So the conclusion is that we can use a 2-sample z-test, meaning we can actually do a hypothesis test. So now we're going to start writing down what our claims are. Looking back at the original problem, we see that the claim is that the death rate due to heart disease is lower for those who took the medication than those who took the placebo. So one of these proportions is P1. I think so far we've designated P1 to be the medication route. So the claim here, if we want to write it down, is that the medication death rate is strictly less than the placebo death rate. A strictly less than symbol means it has to take the place of the alternate hypothesis. So the alternate hypothesis is that P1 is strictly less than P2, which makes the null hypothesis the opposite, that P1 is greater than or equal to P2, where we recognize that the way this has been constructed is that the claim falls at the foot of the alternate hypothesis. And so now the question is, as we run our hypothesis test, can we reject the null hypothesis and garner support for the alternate? Let's find out. The next step of this is to take a look at the nature of the test and find our critical values. Since the alternate hypothesis is written as P1 is less than P2, specifically it contains that less than symbol, we observe that this is a left-tailed test with alpha, the level of significance, 0.01. So if we were to draw a picture of what's happening here, here's 0, there should be some sort of a critical value here on the left, and if we were to highlight the area of this left tail right here, the argument is that the area of that tail should be equal to alpha, which is 0.01. So let's go take a look at the z distribution table, find 0.01 in the table, and then see what the corresponding critical value is to that area. So we're going to erase the work from the previous problem. We want to find 0.01. 0.01 should be somewhere around here. So we notice that between 0.099 and 0.102, our desired area, 0.01, lies closer to the 0.09. So we're going to use that z-score, which is corresponding to a hundredths place of 0.03, and a tenth and a base value of negative 2.3 and a hundredths place of 3. So that tells me that my z-score is actually a negative z-score, and it corresponds to negative 2.33. Because that is the closest I'm going to get to 0.01. So we're going to import that value here. It's actually is negative z-score, a negative 2.33. So what that means is that the rejection region is the highlighted component of that picture, and that's all z values that are strictly less than negative 2.33. So let's take a look at our standardized test statistic and see where that lies on this picture. The standardized test statistic is, well, let's use the formula. All right, that's exactly the formula that we had right here from the previous problem. So what we're going to do is we're going to import that formula. So the answer here is z equals that formulation, where I might pause and remind ourselves that at no point in this computation so far have we used the P1 hat and the P2 hat that we originally computed. That's not necessary until we get to this stage where P1 hat and P2 hat are a component of the standardized test statistic formula. So we did need to compute it. It just took a little while for us to see where we'd use it. In this case, we're going to end up with, well, the numerator is P1 hat 0.0640 minus P2 hat, which is 0.0830. That's the observed difference minus the hypothesized difference, which again, in a hypothesis test is usually 0, all divided by the square root, where P bar was taken to be 0.0731, Q bar was computed as 0.9269, and then we get 1 over the sample sizes. So that's 4,700 plus 1 over 4,300. And the denominator is being square rooted. And if we carefully compute that and round, we should get approximately negative 3.46. Now, as we usually do, we're going to take that standardized test statistic, compare it to our rejection region, and on this picture we see that negative 3.46 probably lives right there. That's where that z-score lives. And we see that it clearly is less than negative 2.33. It lives in the shaded region, so that means that yes, we're going to reject the null hypothesis. So we'll say that since negative 3.46 is less than negative 2.33, the conclusion is that we reject the null hypothesis. What does that mean in the context of this problem? Well, let's take a look at what our claim was. The claim was the alternate hypothesis. We just realized that we can reject the null. If we reject the null, that means we've gathered support for the claim. So writing that down, we're going to say that there is enough evidence at the 1% level of significance to support the alternate hypothesis, which is the claim. So to support the claim, and what is the claim? The claim, as highlighted above, is that the death rate due to heart disease is lower for those who took the medication than the placebo. So we've gathered enough evidence to support the claim that the death rate due to heart disease is lower for those who took the medication than for those who took the placebo. So it turns out that we can support this claim, which is pretty good for the medical research company that hired the researchers, right? That means that their sampling here is actually indicative of a larger observation within the population. And so that means that they have really, really good statistical backing for the success of their medicine. Now, this example is very similar to the previous example that we covered, and it all had sort of a lot of the same moving parts. Going through these two examples in detail should give you the skills and tool set necessary to tackle some of the homework related to Section 8.4. But basically, this is finalizing our conversation in Chapter 8. We've talked a lot about hypothesis testing in Chapter 7. We reintroduced it in Chapter 8 and talked about how to use it to now compare population parameters between two populations. So there's a lot of power of the tools that we've developed so far. This is going to end Chapter 8. If you have any questions, let me know. But otherwise, take a crack at some of the homework. Have a great rest of your day. And I will catch you all later.